We're going to take some notes on trig identities. So I'm going to add that onto our same note sheet we've been plugging along with, this unit circle trig. And if you guys recall, we were doing some graphing like we just reviewed. That was the last thing that we did, right? And so now we're getting down to about our last section, and that would be trig identities. So the term identity means one. Okay, so this has to do something with the number one. And let me give you a little background. You know, what we want to do for a trig identity, let me show you where we're headed, and then I'm going to give you a little background in between there. But what we want to do is we want to take something like 1 plus tan squared x, and we're going to try and condense that down into a single term. Okay, right now it's two terms, of course. So we want to condense that down to a single term. So here's some things that we need for trig identities. First, the single most important thing in a trig identity is the greatest trig identity of them all. And I'm going to show you what that is right now. All right, let's say this is the unit circle. And in the unit circle, the radius, of course, is 1. And so if I was to make a right triangle here, well, the height of this triangle and the base of the triangle we can write in terms of sine and cosine, because remember, cosine is the x and sine is the y. So that means that the length of this bottom is the cosine and the height is the sine, and the hypotenuse, of course, is 1 because that's the radius of the circle. So our man Pythagoras figured out that this squared plus this squared equals this squared. So we could say that cosine of x squared, oh, by the way, I should say, when you write that, it typically is not written this way, although it would be okay. You typically wouldn't say cosine of x quantity squared. That would be okay to write, but it usually isn't written that way. It's written this way: cosine and then the squared and then the x. But what that means is we're taking the cosine of x whole thing and then squaring it. So the cosine of x squared plus the sine of x squared is equal to 1. This, my friends, is the greatest trig identity of them all that you will use over and over and over again. That fact that the cosine squared plus the sine squared is equal to 1. And that comes from the Pythagorean theorem, right, in the unit circle. All right, so how the heck does that happen? How does that help us if, you know, down here we are trying to write as a single function? And I want to write this, the 1 plus tan squared, as a single function. All right, so here's how we start these trig identities. The first thing I think is always the best way to go about it is write everything in terms of sines and cosines. Because remember that tangent is sine over cosine. So that means that tan squared is sine squared over cosine squared. Now I want to do 1 plus that. Well, if I'm going to add fractions, I need a common denominator. So I actually can write 1 as cosine squared over cosine squared. So I rewrote 1 as something that was advantageous to me because I want to combine them. I can always make it something over itself. So the reason we have a common denominator is so that I could write cosine squared x. I'm combining the numerators plus sine squared x over cosine squared x. But remember the greatest trig identity of them all? This one? Cosine squared x plus sine squared x is equal to 1. I can put that as my numerator. So I could write that as 1 over cosine squared x. Well, remembering that the cosine is the reciprocal of the secant, 1 over cosine squared x is secant squared x, and I have written it as a single function.
Wait, I'm confused.
Okay. All right, what we're trying to do is take an original problem here, okay? So now it's 2 terms. We want to write it in terms of sines and cosines so that we can try and combine it so that we can ultimately get it as a single term. Okay, so secant squared x is equivalent to 1 plus tangent squared x. Let me do another example, and then let's see if this helps a little bit. And these are the fact that you're confused. I appreciate you speaking up because I know for a fact you are not the only one. This is confusing. I mean, this is different. Let's say we want to try and write 1 plus cotangent squared x. We want to write that as a single term. So we need to combine them. All right, first things first, write everything in terms of sines and cosines. So I know that the cotangent is the tangent flipped over. So if tangent is sine over cosine, cotangent is cosine over sine. And so I could write that as cosine squared x over sine squared x. And now I want to add that to 1. How could I rewrite 1 so that I could add it to this one?
Sine squared x?
Yes, sine squared over sine squared. I think you're a step ahead of us over here. So yeah, you're right. Very good. So if we can write 1 as anything we want over itself, but it's a great suggestion to write it as sine squared x over sine squared x because now I have a common denominator.
So technically, if you wrote it as cos squared over x, it'd be correct too, but you want to do sine because of the common denominator.
Perfectly put. Yeah, exactly. You could do that. It just wouldn't help you at all, right? So you want to write it as something that is going to help you. So now we have sine squared x plus cosine squared x, which in my next step, I'm going to, of course, write as 1 because I remember the greatest granddaddy trig of them all.
Wait, I don't understand why you would use like cosine sine.
Why we would do here?
No, the first step.
Yeah, okay. So I changed cotangent into that. So we always want to write it in terms of sines and cosines. So remember that the cotangent is the tangent flipped over. And the tangent is sine over cosine, which means the cotangent is cosine over sine. So the cotangent squared is cosine squared over sine squared. So we're using those same trig relations that we had before to write them in terms of sines and cosines. All right, so looking back here, we got down to here where we combined our numerator. And so that's going to then be 1 over sine squared. And sine, the reciprocal of sine squared is cosecant squared. Yeah, so the question was, how did we get from here to here? And that is from this. Because cosine squared plus sine squared equals 1, we have to always kind of keep that in the back of our head. Since cosine squared plus sine squared equals 1, this became 1. All right, great questions today. Anything else? I'm going to do a couple more here.
Why? And then after you get to that part, then why would it like change to secant?
Say that again, Vince.
After we get to 1 over sine squared x, like why would it change to like the?
Yeah, we're just trying to write it in the most concise single term as we can. I mean, it is technically in a single term here. It just looks a little nicer here because it's not a reciprocal. So remember, the reciprocal of the sine is the cosecant, and so we're allowed to write that as cosecant squared x, which is kind of the most concise way to do that. Sam, you had a question? How do you know which one it is? Yeah. So the question was, how do you know which one it is, secant or cosecant? Remember the 6 trig functions: sine, cosine, tangent, cotangent, secant, cosecant. Those 2 are reciprocals. Those 2 are reciprocals. And those 2 are reciprocals. Okay, so the sine and the cosecant are each other flipped over. Same with the cosine and the secant, and tangent, cotangent for that matter. All right, we're doing good here. Let's do another one. All right, let's do the cosecant squared x minus cotangent squared x. So first step, write things in terms of sines and cosines. So remember, we just said the cosecant was the sine flipped over. So cosecant squared is 1 over sine squared. The cotangent squared, cotangent is cosine over sine. So that's going to be cosine squared over sine squared. Well, and lucky us, we already have a common denominator. That's nice. So we can already combine it to 1 minus cosine squared x over sine squared x. Any questions yet? All right, now, what am I going to do with this thing? 1 minus cosine squared. How do I condense that? Remember before we had like sine squared plus cosine squared equals 1, so I was able to convert that into 1.
Wouldn't it be sine squared x?
Oh, why would it be sine squared x? You are correct.
Because cosine x squared plus sine squared x equals 1. So
Awesome.
1.
Great job. Looking at this, and remember I said how important this was going to be, because not only can we use that, we can use any manipulation of it we want to. It is an equation. If I move the cosine squared over, it would be true that sine squared x is equal to 1 minus cosine squared x. So that means I can replace 1 minus cosine squared x with sine squared x. So 1 minus cosine squared x is sine squared x. And that's then over sine squared x. And that whole ugly problem reduced to just 1. All right, let me try one more together. I'm going to have you guys try some on your own. And, you know, I just would encourage you to give them a shot. I do not expect everybody to get them all right. That would be highly unlikely if that happened. But hopefully we can make some strides here. Let's try and simplify, let's say, sine of theta over cosecant theta.
Is it okay if we review the last part of the previous question?
Sure. Let me do that before we get started with this one then. So I'm guessing you mean from here to here. Is that correct?
Yeah.
Okay, yeah. So we have 1 minus cosine squared. Now remember that really important trig identity is that cosine squared x plus sine squared x was equal to 1. We had that written way up high there. So according to this equation, if I moved this over to the other side, sine squared x would be 1 minus cosine squared x. So what I did was replaced 1 minus cosine squared x with sine squared x on top. Okay, and again, because 1 minus cosine squared x is sine squared x, so I made 1 minus cosine squared x into sine squared x.
Okay, yeah, that makes sense. Thank you.
Okay, sure. All right, so to do this one, all right, write in terms of sines and cosines. Well, we already have a sine on top. Cosecant. The cosecant, that is the sine flipped over. So, oh, this becomes a little ugly at first. We have sine theta. And then the bottom becomes 1 over sine theta.
What is that symbol like you're
Oh,
drawing?
that symbol. Thank you very much. Sorry, I forgot to mention that. I was just, that's a variable. So it would just be like x. It is theta, Theta. It's a Greek letter. It is often used in trigonometry, so I thought it would be good to throw it in there because you might see it every now and then. Often used in trigonometry for angle measures, but it's just a variable. And it's written like you draw a circle and then it's got a line through it like that. And so it's part of the Greek alphabet, but it just means a variable. All right, so I wrote the bottom as 1 over sine theta. So now when I take the bottom and flip it over and multiply it by the top, I get sine theta times sine theta, which is sine squared theta. So I have condensed it into a single term. All right, I have just a couple of problems that I want you guys to do on a class kick, and then we're going to go over them together. And you might not get the whole thing. You might just get the first step. You might maybe get the first 2 steps, but just do what you can. Remember, write in terms of sines and cosines. And then if you need to, try and combine to make it into a single term. All right, I will go over, these are the first ones, and you guys seem to do okay. And I know these were the same ones we actually had just done, but it's good practice. First thing, we want to write things in terms of sines and cosines. So I know that cotangent is the cosine squared over sine squared. And so if I want to add that to 1 to get a nice common denominator, I'm going to write that 1 as sine squared x over sine squared x. Well, now I can combine the numerator. Sine squared plus cosine squared is 1. So I have 1 over sine squared x, which is cosecant squared x. The second one is pretty similar. So to do the tangent, I'll write in terms of sines and cosines. So that's going to be sine squared x over cosine squared x. I'm going to add that to 1, but now 1 I'm going to write as cosine squared, cosine squared over cosine squared, so that I have a common denominator. So I have cosine squared x over cosine squared x. So I now, again, my numerator, when I combine them, I get cosine squared plus sine squared, which is 1. So I have 1 over my denominator of cosine squared. And 1 over cosine squared is the secant squared x. So any questions on the first slide? All right. Second slide. We're going to write things in terms of sines and cosines. So the secant is the cosine flipped over. So secant squared is 1 over cosine squared x. Tangent squared is sine squared over cosine squared. I'll let that sink in for a second. And now 1 minus sine squared is cosine squared. So I have cosine squared x over cosine squared x, which of course is just 1. So remember, again, here I'm using that rule. You know, we know that cosine squared plus sine squared equals 1. So if I move that over, I know that cosine squared is equal to 1 minus sine squared x. So since 1 minus sine squared x, I can replace that with cosine squared I took 1 minus sine squared and replaced it with cosine squared. All right, last but not least, this theta is freaking you guys out. All right, just because we haven't seen it before. Guys, it's just a Greek letter that mathematicians love to use in trigonometry, and it just means a variable. So if it helps you to do this, you can replace it with an x. It means the exact same thing. It will be exactly the same as if we wrote that as tan x times cotangent squared x, okay? But it's good that you've been exposed to it. Again, it's pronounced theta, and you'll see it. So now that we've seen it, just remember it's just a variable, okay? So to solve this, I want to write things in terms of sines and cosines. So tangent is sine x over cosine x. And the cotangent is cosine over sine, so that's going to be cosine squared x over sine squared x. All right, well now, these things I can cancel. Like I can cancel a cosine here and a cosine there, just like if you had like, y squared over y, you would cancel one from each. And I can cancel a sine there and a sine there, which leaves me with cosine x over sine x, and cosine over sine is the cotangent. And so our answer is cotangent of x. All right, we doing okay here? Any questions on that second slide?